Watch this. A laptop is generating an answer with a model that contains nearly 700 billion parameters. No server rack beside it, no massive GPU setup, just an ordinary computer, a limited amount of RAM, and an SSD. It sounds impossible, and technically, it is running locally. But there is a catch. The laptop is not loading the entire 700 billion parameter model into memory. It is not calculating every parameter for every word. And depending on the demonstration, some of the work may not even be happening on the laptop. So how can a model this large run on a normal computer at all? The answer is a stack of compromises: quantization, mixture of experts, CPU and GPU offloading, and, in the most extreme cases, streaming model weights directly from an SSD. These tricks make local inference possible, but they do not make it fast. To understand the trick, we first need to understand why a 700 billion parameter model should not fit on a laptop. A parameter is essentially a number stored inside the neural network. During inference, the computer repeatedly reads these numbers and uses them to transform your input into the next predicted token. If every parameter is stored using 16 bits or 2 bytes, then 700 billion parameters require roughly 1.4 terabytes just for the model weights. That does not include the context cache, temporary computation buffers, the operating system, or anything else running on the machine. Clearly, a laptop with 16 or 32 gigabytes of memory cannot hold that. Even a powerful desktop GPU with 24 gigabytes of VRAM is nowhere close. So the first trick is quantization. Most large models are trained using relatively precise numerical formats. But after training, their weights can often be stored using fewer bits. Instead of representing each weight with 16 bits, you might reduce it to 8 bits, 4 bits, 3 bits, or even close to 2 bits. At 4 bits per parameter, a 700 billion parameter model falls from approximately 1.4 terabytes to around 350 gigabytes. At 2 bits, the theoretical weight size approaches 1 gigabytes. Real model files are usually somewhat larger because they contain metadata, scales, higher precision layers, and other information. But the reduction is still enormous. Quantization does not simply delete random information. Modern methods can preserve sensitive parts of the network at higher precision while compressing more tolerant parts aggressively. The result is a smaller model that behaves similarly to the original, although quality can decline as the compression becomes more extreme. But even after aggressive quantization, we still have a problem. A model file larger than 150 gigabytes does not fit inside 32 gigabytes of RAM. Quantization makes the impossible smaller. It does not automatically make it fit. The second trick comes from the architecture of the model itself. Many extremely large models use something called mixture of experts. Imagine that instead of having one giant neural network process every token, the model contains many smaller specialist networks called experts. One expert may become useful for code. Another may respond strongly to mathematical patterns. Others may specialize in language, reasoning, factual relationships, or more abstract patterns that humans cannot easily label. Before each token moves through an expert layer, a small router examines it and selects only a few experts. The important point is that most experts remain inactive. A model may contain close to 700 billion total parameters, while only a much smaller fraction is activated for each token. That means the full parameter count describes everything the model can potentially use. It does not describe how much computation happens simultaneously. This dramatically reduces the amount of mathematics required for each generated token. But there is a common misunderstanding here. Inactive parameters do not disappear. The computer still needs access to their weights because a different token may activate a different set of experts. Mixture of experts reduces computation. It does not automatically eliminate storage. And it does not mean that a 700 billion parameter model suddenly becomes a normal 30 or 40 billion parameter model. All of the experts still need to exist somewhere. That somewhere is usually system memory, GPU memory, or storage. This leads to the third trick, offloading. Normally, you want model weights inside GPU memory because GPUs can read and process them extremely quickly. But when the model is too large, inference software can split it across different devices. Some layers may live in GPU memory, others may remain in system RAM and be processed by the CPU. The GPU can handle layers that benefit most from acceleration, while the CPU handles whatever does not fit. This is why someone with a 24 gigabyte graphics card and 64 gigabytes of RAM can sometimes run a model much larger than 24 gigabytes. They are not fitting the whole model on the GPU. They are dividing the work. On Apple Silicon, the CPU and GPU use a shared pool of unified memory, which can make this division somewhat simpler. But the same limitation remains. If the model is larger than the total available memory, something still has to stay outside it. That brings us to the SSD. Inference engines can use memory mapping to treat a model file almost as though it were part of memory. Instead of copying the entire file into RAM, the operating system loads the required sections when they are accessed. For a dense model, this does not solve much. A dense transformer needs to read almost every layer for every token, so continuously pulling weights from storage would be painfully slow. But a sparse mixture of experts model creates a more interesting possibility. The small shared parts of the model can remain in RAM. Then, when the router selects particular experts, the engine can load the required expert weights from the SSD. The rough cycle becomes select the experts, read their weights, perform the calculation, discard or cache them, and repeat for the next token. The computer is no longer holding the whole model. It is holding a working set. This is the key behind many 700B model on a laptop demonstrations. The model exists locally as a huge collection of files. Only the sections needed at that moment are brought into fast memory. Technically, the laptop is running the model, but it is not running it in the way most people imagine, and storage speed becomes the main bottleneck. RAM bandwidth can reach tens or hundreds of gigabytes per second. High-end GPU memory can move data at hundreds of gigabytes or even more than a terabyte per second. A consumer SSD is much slower and has far higher latency. If several gigabytes of new expert weights must be read for every generated token, the laptop may produce only a fraction of a token per second. That could mean several seconds for one token and much longer for a complete sentence. The prompt processing stage may be even more painful because every token in the input must pass through the model before the answer begins. Caching can help. Recently used experts may remain in RAM because nearby tokens sometimes activate similar experts. The operating system may also keep frequently accessed sections of the model in its page cache. More RAM means a larger cache. A faster SSD means weights arrive sooner. And a GPU can accelerate the portions of the model that remain resident. But none of these techniques remove the fundamental trade-off. When you replace fast memory with slow storage, you pay with time. So when someone says a 700 billion parameter model fits on a laptop, the more accurate statement is this: a heavily quantized copy of the model can be stored on the laptop, while a much smaller working set is moved through memory during inference. That is impressive, but it is not the same as loading the entire model into RAM and chatting with it at normal speed. There is also another possibility you should always check: remote inference. A local interface does not prove that the model is local. Desktop chat clients, web interfaces, and command line tools can send prompts to an external API while looking almost identical to software performing local inference. To verify a demonstration, disconnect the internet. Check whether the complete model files are stored on the device. Watch network traffic. Monitor RAM, CPU, GPU, and disk activity. If the model responds instantly while using almost no memory, processing power, or disk bandwidth, there is a good chance the real computation is happening somewhere else. So is running a huge model this way actually useful? For an ordinary chatbot, usually not. A smaller model that generates 20 tokens per second will often be more practical than a frontier-sized model generating one token every several seconds. You would not use SSD stream inference for a live voice assistant. You would not want it powering autocomplete while you type. And long context windows could require even more memory for the KV cache, separate from the model weights. But speed is not always the only priority. A slow local model may be valuable when the data cannot leave the machine. It may be useful for experiments, offline research, model analysis, or long-running jobs where you can submit a task and read the result later. You could give it a difficult code review, a large document analysis task, or a research prompt before going to sleep. Then come back later and inspect the result. That is a very different experience from using a normal chatbot. But it is still real local inference. It also proves something important about the future of local AI. Model size is not a simple wall. It is a trade-off between storage capacity, memory bandwidth, compute power, compression, and time. Add more GPU memory, and more layers can remain on the GPU. Add more system RAM, and more experts can stay cached. Use better quantization, and the model becomes smaller. Use a faster SSD, and disk streaming becomes less painful. At one end of the spectrum, you have a data center generating tokens almost instantly. At the other, you have a laptop slowly pulling experts from storage. The model may be the same. The experience is not. And that is the catch. You can run a nearly 700 billion parameter model on a laptop, But the laptop is not loading all 700 billion parameters into memory at once. It is not activating all of them for every token, and it is not delivering the speed you would expect from a normal AI assistant. The weights are compressed, most experts remain inactive. The workload is divided between the GPU and CPU, and whatever cannot fit in memory waits on the SSD. The laptop is not carrying the entire model in its hands. It is repeatedly reaching into a giant library, pulling out the few pages it needs, using them, and putting them back. That is slower than keeping the entire library on the desk. Much slower, but the fact that it can be done at all is remarkable. A model that once required racks of specialized hardware can now, with enough compression and patience, produce an answer on an ordinary computer. Not quickly, not without compromises, but locally. So yes, a laptop can run a nearly 700 billion parameter model. The catch is that the model never truly fits inside it, and you pay for that with speed.